Hello everyone. According to Wikipedia, the hardware cost for a single AlphaGo Zero, which is the Go Play neural network that has been developed in 2017 by Google DeepMind, including the four TPUs, which stands for Tensor Processing Unit, which is used within the deep learning, has been quoted as around 25 million United States dollars. So, in this regards, I have at least two questions. So the first one is, why is that so expensive? And second is, what can I achieve at home for free on the laptop that is beyond average? So yeah, these numbers are quite huge, definitely more than a single laptop without any GPU and just two CPU cores. And below here goes the explanation, like how do they calculate the cost for the training process, assuming this rate for the TPU per hour, right? And eventually, here is the table where they show like the eventual results they have come up with. So there were two experiments. So the first experiment, like with a smaller data set and a shorter training process, it only took like $2 million, and the wider and the wider experiment took $35 million, which is absolutely insane number. Okay, guys. So, but anyway, quite interestingly, so we still can kind of try to walk through this exact experience without spending that enormous amount of money. So there is a fantastic project called Alpha Zero General, any game, any framework, created kindly by Surag Nair. I'm sorry if I'm pronouncing his name wrong. So this guy has implemented the Alpha Zero algorithm as it has been presented in the paper by Google DeepMind. The project structure is nested here and a little bit complicated. So what I did is I just simplified this a little bit, and I just extracted those necessary files that I need to use to train the network for the game of Go. And one of the most critical parts here was to provide the logic to the game of Go. So essentially, I needed to implement the Go board, and this should be like handling captures, the end of game state, which is quite an interesting thing to bear in mind. I'll talk about this just in a moment. And essentially, I came up with this sort of a setup. This repository will be public by the time you're watching this video. So earlier on this channel, I've made a series on how to make a Go playing program in Python. And well, this is pretty dumb AI, to be very honest. This was the implementation of the 1981 Go playing program called Wally, and that was originally running on King 1, believe it or not, the very old 6502 based computer. So I've reused the code that I've written for Wally. I've improved the code. I've added some functions to calculate territory. But this code, which you could have been following during the series, I've used this code to represent the game rules. One of the most essential and most critical parts, I would say, is this function get game ended, because for the algorithm to learn properly, it needs to know exactly when the game has ended. And when it comes to the game of Go, uh, already some challenges are arising, because usually the game of Go is ended when both players agree that the game has been ended. But how on earth would you actually define that? So two subsequent passes are usually leading to that. But how do we know when it's time to pass? And well, essentially, when there is no territory that doesn't belong to anyone. So essentially, when you can only have white territory or black territory, and maybe some death stones, but anyway, so if you don't have any unexploited territory, that means that the game is decided already. Okay, so now let's have a look at the neural network architecture. So I essentially took the neural network from the game of Othello, and this might not be the best ever choice, but it has some interesting features like the game can be win, loss, or a draw. Well, although in Go, because of the Kami, we don't particularly have a draw, and especially on the 5x5 board, yeah, it's really hard to imagine how to draw the game. But anyway, so this architecture seems to be working quite nicely. Now let me show you the main file called train.py. So the parameters here are interesting. So these are the values from the game of Othello. I'm using my own values. So the number of iterations is equal to 10. But again, it's not just 10 iterations and that's it. So I'm just running the cycles, 10 iterations each. Currently, now on another laptop, I'm running the iterations from 80 to 90. It takes around 5 hours and 20-30 minutes to run the training process with this specific parameters. So, and every time it plays slightly better than the previous version. So, number of iterations is 10, number of episodes is 10, and this number is quite interesting. So, I've been experimenting with 100s, like they suggest, but with such big numbers, I don't know, something goes wrong with the training process, and the neural network doesn't improve that nicely as it does when I only play 10 games per one iteration. So, like one iteration, 10 games, right? And then the number of episodes I use to train the neural network is 3. So if I do neural network epochs, the number of epochs is 3. So it plays 10 games, then it trains the neural network for 3 epochs. Okay, so now let's have a look at the script where we can play match. So first, a random Go player will be playing with black stones and our neural network with white stones. That would be 10 games. We'll print the results and then we'll swap the players and let them play vice versa. So let's have a look. So I just do Python 3 play old versus new, and here we go. If the game goes too fast, feel free to pause the video and to see the position. But anyway, already zeros, which stands for white stones, occupies the center and tries to split black groups. Black is playing very fast because that's the random player. Anyway, so should have killed. Yeah. Oh, unfortunate, very unfortunate game here. So the first game, when neural network actually lost to random player. Well, things happen from time to time. But anyway, you just have a look at the intelligence. It's trying to split the groups of black. So X's are black, zeros are white. So white are trying to split black, which is good. And yeah, let's have a look. All right. So now we have the result -1. Cool. So this is the final position. So total crush. Okay. And again, the same. You see, like the neural network, and likely the random player, is trying to occupy the center and split the board into 2 parts. So that's the sign of the intelligence already, even after only 10 iterations, 10 games self-play each. Again, we have another fantastic result. So it make 3 eyes, black only made 1, and this would die anyway. So another Russian win. Okay. So yeah, it defends the capture, which is cool. And although, yeah, this can be still captured here, for instance, and it's not perfect really, but anyway, yeah, the games are going a little bit too fast. But still, you just have a look, it still wins. So this stone is dead. sort of knows about it, so it's totally fine. Yeah, cool. So, well, definitely we see the improvement of the neural network over the random player, which is already really good. So I should have played here to capture. Oh, it just captures like this. All right. Okay, and another crushing win. So yeah, wins most of the game. So just lost the very first game. All right. And then we'll swap the colors, swap the players. But still, you see, like it does the same thing. This is so cool. Another crushing win. Here is the final position. And that's because it has one, and this has nothing, and both groups are actually dead. So that's the game ending condition I've been mentioning earlier. And again, so white makes two eyes. This is fantastic. Can you believe this? Already knows about eyes, seemingly, after just 10 iterations. So he attacks this stone, but not being in a hurry that much to take it. It instead, oh, she didn't. Yeah, but it would capture this group instead. What a fantastic game. Oh, captures everything, yeah. Oh, randomly playing the best move. Okay. Yeah, this gets really harder to deal with when opponent, even though he's a random player, he occupies the center. It gets really harder to achieve the result here. Yeah, almost impossible to win, but since the random player doesn't know that he needs to capture, then yeah. But anyway, it's probably would still, yeah, it still wins. Just because of this 4 random moves in the center, it just wins, which is so cool. Yeah. Okay, so neural network won 9 games, lost 1 game. Yeah, it actually lost 2, I think. So maybe there is something wrong with the counter. Okay. Um, and no draws. Okay, now let's try to swap the players, and we will have neural network being playing as black. And let's have a look. Yeah, not the best ever move, but still tries to play in the center. Then quickly recovers. It would start playing in the center over the next iterations. For now, unfortunately, it doesn't. Oh, it lost the very first game. Yeah, whoa, lost the first game. Yeah, for some unknown reason, I've noticed that neural network actually plays better with white stones, which moves second, which is strange, but yeah, that's the truth. So yeah, it's about to lose again. Whoa, lose 2 times to the random player. Yeah, that's unfortunate. That's very unfortunate. Yeah, random player, random player rules. Okay, finally placed in the center. So this should do the trick. Yeah. Okay, tries to make some territory. Okay, this should actually win. This should win. Yeah, this wins. All right. Yeah, starts playing in the center. That's way smarter than playing not in the center, because on the 5x5 board you need to play in the center and split the board into 2 parts. Whoever achieves that will win the game. Right? Oh, that was not clever, but still wins. All right. But anyway, we clearly see that neural network, although it's still very, very dumb and no reason to play versus it as a human player because we just lose every single game. But yeah, it's playing better than the random player, which makes perfect sense to me. Yeah, these moves on the ball edge are absolutely pointless, so it would probably lose. But on the other hand, when you watch the games, I've been watching lots of games like this. Oh, well, that is possible only versus the random player, to be honest. Um, the way how it learns to play on 5 by 5 boards, sometimes it looks like that the board size doesn't matter for the network. Like it's not trying to be just tactical, just to search like a brute force search and just trying to kill everything. No, it's trying to have some strategy, to apply some strategy. It's trying to either make living groups, even on this small board size. It tries to split opponents' groups. So it actually applies all those strategies that Go player needs to. Okay, lost. The Go player actually needs to apply in order to win on a bigger board size. And again, it's really so exciting to watch how this happens on this tiny little board. But yeah, because of the small size, we can still sort of enjoy the relevant improvement over every next 10 iterations. Okay, now again, it just tries to split the board into two parts, and this strategy, yeah, splits the board into two parts, and this strategy works always, just always works, but not, but not for this network. Anyway, neural network wins 8 times and loses twice. Okay, guys, so within the next videos in this series, we are going to be watching the games of newly trained neural network versus the old one. So every next neural network would be trained 10 iterations more, and that would be good enough to win versus the previous version that has been training like 10 iterations less. That's it from my side. Thanks for watching, and I'll see you in the next match.